In today's class, we will study about the torque due to a current loop in an external magnetic field. In the previous class, we have learned that a closed loop placed in an external magnetic field will experience zero net magnetic force. So, however, we are going to see whether this loop is going to experience any torque. Okay, the coil is PQRS. It is placed in an external magnetic field which is directed from the north pole to the south pole, as you can see in this figure. What we will do first of all is we will analyze the forces on each of these elements, and then we will find out the net torque due to these forces. Let L be the length of this side, length of this rectangular loop, and B is the breadth of the rectangular loop. L is the length of the rectangular loop and B is the breadth of this rectangular loop. Okay, let us take the first one. The force on PQ. The force on the element PQ. Okay, you can see that this is the direction of current on PQ, and let me say the magnitude of this current is I. Now you can see this is the length PQ. Now this is the direction of the magnetic field. Now the normal to PQ makes an angle theta. I repeat, normal to PQ makes an angle theta, which means the normal, this is the normal. This angle is theta, this angle is 90 minus theta. Normal makes an angle theta. This is normal. Normal makes an angle theta with the direction of the magnetic field, which means PQ will make an angle. This angle is theta. The total angle is 90. That means the angle made by PQ with the magnetic field is 90 minus theta. We have the formula for magnetic force is equal to BIL. In this case, the length is equal to B. BIB sine of the angle between the current element. Current element is likewise. This is current element. This is the direction of current, and the angle between them is 90 minus theta. Now I will say this is BIB cos theta. Let us take the situation number 1. Now the question comes, what is the direction of this one? Which can be determined using the left hand rule. This time around I am not going to keep them mutually perpendicular, but I am just considering the angle, right? So this is the direction of the magnetic field. This is the direction of magnetic field. This is the direction of the current element PQ. This is the direction of the current element PQ. This is the direction of current element PQ. This is the direction of the magnetic field. And you can see that the thumb is directed vertically downwards, correct? This is the direction of PQ. This is the direction of magnetic field. And you can see that the thumb is perpendicular, which means this force is acting downwards. Force on PQ. I will say this is FPQ. Now, with your permission, the job of this one is over. Now we will take the next one. What will be now in the similar way we can find out the force on SR. Force on SR, direct it is. The force on SR is BIB. Now look, this is the direction of the magnetic field. This is the direction of not force on SR, it is force on RS. Force on RS. R is likewise, S is likewise. Now this is the normal. This angle is theta. This angle is 90 degree. This is the direction of IB. The current element is likewise. You can see the direction of current. The direction of current is likewise. So this case, this is the direction of IB. IB is in this direction. So BIB. What is the angle now between? See, what is the angle between the magnetic field vector and the current element vector. This much is 90, this much is theta. So this is sine 90 plus theta. Sine 90 plus theta. How it is 90 plus theta? So this angle should be the angle between the magnetic field vector and the current element vector. You have to understand. So the angle, sine of the angle between the magnetic field vector and the current element vector. Since current is in this direction, current element is in this direction. Now this angle is already told us theta. This is 90. Total is 90 plus theta. So this will give you the answer as BIB. Sine 90 plus theta is cos theta. Now let us consider the direction of the magnetic force. Magnetic field is directed that direction. This is the direction of the magnetic field. This is the direction of the current element. And look at the thumb. In which direction the thumb is oriented? Thumb is vertically upwards. Which means this force is upwards. And you can see that both are the same magnitude, which is equal to. Now with your proportion, that itself is equal to FPQ in magnitude or minus FPQ in vector symbol. I have shown direction. So FRS is minus FPQ. The question, can these forces rotate this one? This is the direction of FRS. This is the direction of FPQ. Question, can this cause the rotational effect on this loop? Can these forces rotate the loop? See, I am pulling likewise and I am pulling likewise. This will it cause a rotational motion? I don't think so. So these two forces cannot cause any torque about this axis because forces along the axis of rotation, or forces parallel to the axis of rotation will not create any torque. Forces parallel to the axis of rotation will not create any torque. This is force on axis. Now the next job we are going to see is force on PS. Force on PS. FPS. Force on PS. Now you can see here, see on the board, force on PS. PS is, okay, I should say not PS, it is FSP. The direction of thumb is from S to P, so I am saying FSP. This is the direction of current, right? Which is the direction of the magnetic field? It is right towards, this is the direction of the magnetic field. Now tell me, what is the expression for the magnetic force? What is the expression for the magnetic force? It is B I L. What is the angle between magnetic field vector and the current element vector? You can see from this diagram, what will be the angle? What will be the angle? What will be the angle? Angle between IL and B. Angle between IL and B. What is the angle? 90 degree. This is sine 90. BIL sine 90. And what is the direction of this force? Now you can easily find out. This is the direction of the magnetic field. This is the direction of IL. So you could see that the direction of the magnetic force is outwards. This is outwards. Outwards. This force is acting outwards. Yes. Then what is the force on QR? Now it is very simple job. Because what's the difference between these and this is that the direction of current is reverse. Now I am going to take that into consideration. Okay, whatever I intended to do, that only didn't happen. Yes, again we can see that the angle between the magnetic field vector and the current element vector is 90 degrees. So this is BIL sine 90. But this time what is the direction of the current element? current element is upwards, magnetic field is right towards, and the magnetic force is into the plane of this board. When you draw in your notebook, it is into the plane of your notebook, and this is acting into the plane. See, and this is equal to minus F. Yes. Sorry, minus Fst. Now you can see that how we got net force is equal to 0. These two forces are equal in magnitude but opposite in direction. These two forces are equal in magnitude but they are in the opposite direction. So that means the net force, when you take the vector sum of all four forces, net force is equal to 0. Net force is equal to 0 when you take the vector sum of the forces. Now the question, can this cause a turning effect? See, Fs is out of the board. See, this is the thing. It's outwards. So what I am saying is that here it is pulled. Okay, just like I am taking this pen as this loop. It has got a small plane, although not like what it is here. Now I am pulling it outwards. I am pulling this part outward. I am pulling this part inward. So you can see that there is a turning effect. Can you see this? I am pulling this part outward. This is inward. So it is creating a turning effect like this. So you can see from this figure, the two forces on this one is causing a turning effect like this. This is the turning effect. Turning. Okay, I am taking your attention to the next page. This is the direction of the magnetic field. Okay. This is the direction of the magnetic field. This is what I said. This is SP. Here you are seeing that the force is directed outwards. The force is directed outwards, or rather force is perpendicular to the magnetic field. Assume that this is perpendicular to the field. 90 degree. Now this is the other thing, which is what? QR. And you can see that on this part, the force is into the plane. And again, I am considering that this is perpendicular to the magnetic field. These two forces are equal in magnitude. I am saying F itself, this angle is 90 degree. Now see, this length is B. This angle is 90 degree. This angle I said as 90 minus theta. Then what is the total length between these two points? I am saying say O and X. What will be the length OX? Length OX. This is B. So cos 90 minus theta is equal to now this angle is 90 degree. OX divided by OF, which is OX by B, I can say. Or OX is equal to B cos 90 minus theta is sin theta. This is B sin theta. B sin theta. Now why did I calculate this one? Now I am showing it. This is one force. This is another force. These are points, acting points are O, X respectively. Then this is the perpendicular distance between the line of action of two equal forces. 90 degree, 90 degree. This is force F, this is force F. Now what you see here is two equal and opposite forces. Two equal and opposite forces whose line of action is separated by a perpendicular distance. We used to call it by the name a couple. These two forces now form a couple with the torque is equal to OX into F. OX into F. OX into F. OX into F. Now OX is equal to B sin theta. F is equal to BIL. F is equal to BIL. F is equals BIL. Now we can see that this is equal to I into LB sin theta into B. ILB sin theta into B. Now what is L into B? This side is L, this side is B. L into B is what? The area of this loop. L into B is the area of the loop. Now now I got I into L into B. L into B is area, I is the current. I am going to define a new variable, that is magnetic moment or magnetic dipole moment, we say. Generally when it comes to a bar magnet, this will be defined as magnetic dipole moment. At present I call it by the name magnetic moment, and the formula for magnetic moment M is equal to I into L into B. Okay, not the time to put the bracket. This is equal to I into A. I into A, because A is the area of the loop. M is magnet. It is the product of current and the area of the loop. The product of current and area of the loop is what is called the magnetic moment. Okay, let us come back to this discussion. So I into L into B, I can put as M. So torque toe is equal to MB sin theta. The magnitude of the torque toe is equal to MB sin theta. Magnitude of the torque is equal to MB sin theta. Now we need to D. Okay, so the next question comes is, suppose I got, okay, I am taking the loop down this sense. Just for our convenience only. This is the direction of the current we said, and this is the direction of the magnetic field. Now we need to see whether the torque is M cross B or B cross M. We need to see whether the torque is M cross B. Is it M cross B or is it B cross M? Is it M cross B or is it B cross M? This is the question to be answered now. See, how to determine the direction of the magnetic moment? Very simple rule for a closed loop. To determine the magnetic moment, we have a very simple rule. That is also called the right hand rule. If you curl the fingers of your right hand in the direction of current, curl the fingers of your right hand in the direction of current, thumb will represent the direction of magnetic moment. So we repeat it. Curl the fingers of your right hand in the direction of current. Thumb will represent the direction of magnetic moment. Curl the fingers of your right hand in the direction of current. Thumb will represent the direction of magnetic field. Magnetic moment, I'm sorry. So okay. So here magnetic moment is out of the plane of the board. Now we need to see the whether the formula. We got torque is equal to MB sin theta. Now the job that is in front of us is to see whether it is M cross B or B cross M. In vector form I need to write. Okay, M is directed out of the board. B is rightwards. We need to get the rotation in the sense, that is what we have seen just before. M is outwards, B is here. So I am going to first take B cross M. B is in this direction, M is in this direction. B cross M means sense of rotation. Likewise, see, this is the sense. This is the sense. Is it the sense mentioned here? The sense is likewise here. Now decrosum means decrosum is likewise. Is decrosum satisfy our requirement? Is decrosum, this is B, this is M. Decrosum give you the sense of rotation likewise. Decrosum is giving a sense of rotation likewise. That is wrong. Because we have seen the sense of rotation likewise, which means M cross D. The sense of rotation is likewise, so that means torque cannot be decrosum, it has to be M cross D. So this is the expression for the torque experienced by a current loop in an external magnetic field. External uniform magnetic field. And you can recollect this formula with what we have learned in electrostatics. There we have studied P crossing. P is electric dipole moment. Analogous to that we have M, magnetic dipole moment. P crossing, electrostatic field. B, magnetic field. So both these formula are complementing each other, I should say. So torque experienced by a current loop is equal to tau is equal to M cross B. This is a torque experienced by a current loop in an external field. And let me tell you, likewise I said with electrostatics, this torque is a restoring torque. The torque experienced by a current loop in an external field is a restoring torque. Therefore, we say the torque has a magnitude minus mv sin theta. Minus mv sin theta. The reason for this minus is it is a restoring torque. The reason for the minus is it's a restoring torque. The reason for minus b is a restoring torque. Now take a situation. If theta is small, sin theta is approximately theta. In that situation, I will get tau is equal to minus mv theta, which is equal to I alpha. What is I stands for? I stands for moment of inertia of the loop. Moment of inertia. Sorry, not inertia. So moment of inertia of the loop. Moment of inertia of the loop. I is the moment of inertia of this loop, current loop. I is the moment of inertia of the current loop. From here I will get alpha is equal to minus mv divided by I into theta, which is equal to minus omega square theta. You studied in chapter number 14 of class 11 SHM. This is executing angular SHM, which will give us omega is equal to root of mv divided by I, or time period is equal to 2 pi by omega, that is 2 pi into root of I divided by m. This is the expression for the time period of small oscillations of a current loop in an external uniform field. I told you already, current loop experiences zero net force only in an external uniform field. Current loop experiences zero net force only in an external uniform field. I hope this class is clear to you. Study well. Thank you.